This is the video lesson for Thursday, February 17th, our statistics notes day 3, and we are going to be examining linear, quadratic, and exponential models. So if you look at the top, it says, suppose you record the high temperatures for each day of the year. If you want to model this data with a function, how would you decide whether to use a linear, quadratic, or exponential model? In real-world applications, the function that describes a physical situation is not always given. Finding the function is an important part of solving problems. In our exploration of these models, we will also use graphing technology to help us find them. And we'll get into what is called linear, quadratic, and exponential regression, but that will happen next week. So today we just want to examine the 3 base models. At the top, you are already familiar with linear and quadratic models, and you can see y equals mx plus b and y equals ax squared plus bx plus c. The exponential model will be y equals a times b to the x. It's obviously called exponential because we have a base raised to an exponent, b raised to the x. And actually, our next chapter that will start in quarter 4 is going to examine exponential functions. As far as an example, you can see y equals 2x plus 3, y equals x squared minus 1, and y equals 2 to the x. And you see the appearance of a line, a parabola, and a curve which is growing. As x gets larger, y is getting larger exponentially. The model there is called an exponential growth model because as x gets bigger, y gets bigger as well. In an exponential decay model, as x gets bigger, y gets smaller, and a graph falls from left to right. So now, tables. One of the ways we can determine from a table which type of model we have is based on what's happening with the x and y variables. When the x variable changes by a constant amount, so in our linear model, you can see -3 to -2 is increasing by a positive 1. -2 to -1 is increasing by positive 1. -1 to 0, positive 1. And that pattern continues for the entire table. As long as the table is showing an increase by a constant amount, then we can then look at the y values, and in a linear model, the first difference, the difference between those y values should be the same. So for instance, -3 to -1, if you take the second value and subtract the previous, -1 minus a -3, you can see we have a positive 2 increase. From -1 to positive 1, it's also a positive 2 increase. Again, if you weren't sure, you could subtract the first value from the second. Of course, 1 to 3, 3 minus 1 is positive 2. 5 minus 3 is positive 2. And 7 minus 5 is positive 2. And that's the pattern you're going to see with the first differences in a linear table where the x values are changing by a constant amount. So that's how the table can indicate to you a linear model. For quadratic, it's the second difference that tells us it's a quadratic model. And quadratic models, sometimes you can have the same value appear for y in the table more than once because of the nature of the graph being a parabola. That will not be the case with the linear or exponential models. So as I take a look, 3 minus 5 is actually, that difference is -5. 0 minus 3 is -3. -1 minus 0 is -1. 0 minus a -1 is actually a positive 1. and 3 minus 0 is a positive 3. So I don't notice the same first difference like I did in the linear model, but now if I take the second difference, notice what happens there. So negative 3 minus a negative 5 really means I'm increasing by a positive 2. Negative 3 to negative 1, well, negative 1 minus a negative 3 is also an increase of positive 2. 1 minus a negative 1 is an increase of positive 2. 3 minus 1 is an increase of positive 2. So it's the second difference in a quadratic model that will be the same. So you look at the first difference. If it's the same, that means the model is linear. If the first difference is not the same, then you look at the second difference. If it's the same, the model is quadratic. For exponential models, the first difference won't be the same, nor will the second difference. What is the same is what the value you're multiplying by is. It's called the common ratio. If we take the y value over the previous y value, so as my x values are increasing by a constant amount, that's true of all three models, my y values, notice 1 times 2 is 2, so I'm actually multiplying by 2. 2 times 2 is 4, so I'm multiplying by 2. 4 times 2 is 8. So that common ratio, you can see between all values, we're multiplying by 2. We actually find it by taking, the y value of 2 over 1, and the y value of 4 over 2, the y value of 8 over 4, 16 over 8, and 32 over 16. Sometimes with exponential models, especially when output is fractions, it's just best to take the ratio of one value over the previous value. And sometimes it's obvious, like here, you're multiplying by 2 each time. But the common ratio is the same in exponential models. Where do we use these types of models? Well, in linear models, under word problem, you see where the values are growing or shrinking at a steady rate. That's really important. Money per hour, you have a starting amount, that's usually B. That's where you have a linear model. Quadratic models are often used in projectile motion when you're throwing or dropping an object, like a ball being kicked or something, or area for geometry. And then exponential models are usually used with interest where money is growing or decreasing and population is growing or shrinking over a period of time. So those are just some of the main places you'll see these models used. So if we move down to the second page, the back side, it says, consider the 3 scenarios below. Match each with the corresponding function, graph, or table. So I'm going to pick pink again. It says, Mariella is driving home from her vacation spot at a constant rate. Which function, graph, and table represent her distance from home as a function of the number of hours she has traveled? Explain your reasoning. So if you're confused on which model that might represent, a couple key things. She is traveling at a constant rate, and obviously when she leaves her home, the distance that she starts at is a set value that doesn't change. So let's keep that in mind when we look at example B. In B, a mechanic drops a wrench from a flying helicopter. Which function, graph, and table represent the height of the wrench above the ground as a function of time since it was dropped? And again, from what we just saw above, that is looking like projectile motion as the wrench is being dropped from the helicopter. So that makes me inclined to think that the model is quadratic. And then the third model, it says scientists watch as a single cell divides into 4 cells over the course of an hour. During the next hour, each of the 4 new cells divides into 4 cells and the process continues. That's making me think exponential because it's growing by a multiple of 4, and A is making me think linear. So if I was trying to think about it, linear, quadratic, exponential. That's how I would be thinking about those models. So at the bottom, for A, which I think is the linear model, I need to find the equation that looks linear, and that would be h of x. So here I would put h of x. As far as the graph that is linear is graph 2. And the table is the one that's tricky. I'm looking for the table that's showing the same first difference. And so as I look at the tables, my first table to me is looking like multiply by 4. That just jumps out at me as I look at those values. These values I have to subtract and are maybe a little harder to find the first difference. So I'm going to go to the third table, and 350 minus 450 would be negative 100. 250 minus 350, negative 100. 150 minus 250, negative 100. And 50 minus 150, negative 100. So my inclination there is that table 3 is the linear model. I didn't find the differences, but let me find them. The 1836 minus the 1900, I believe, is negative 64. Oops, I need to write a little smaller. So that's negative 64. Then the next one, 1644 minus 1836 is negative 192. Then 1324 minus 1644 is negative 320. And then the last one is negative 448. So if we then go back and find the second difference, we can show that that second difference is negative 128. And so that helps me know quadratic. All right, so let's do the others. For B, that was the model I thought was quadratic. As far as the function, the f function, f of x, is a quadratic model because of the x squared. It can be written in the form ax squared plus bx plus c. The quadratic graph would have to be graph 3, and the table would be table 2, which leaves us with example C, which I think is exponential, and that makes sense. G of x is the exponential function. Graphically, that would be graph 1, and that would be table 1. So there you have it. So what you are going to try to do in your homework, which it can be found in Canvas and you can upload it there, I have it uploaded here, is you're going to download this worksheet. You can either print it off or you can upload it to Canvas and complete it there, but you want to complete the key at the top. I already, in Notability here, picked 4 colors for linear, exponential, quadratic, and neither. And so let's say I'm looking at quadratic. I can look at my equations and see where I might have a quadratic model. So this is a quadratic model, so I could color this square in green. Then if I'm looking at a graph, this graph right here looks quadratic, so I could color that. Of course, I could be neater, but you get the idea. And for each of these, you've got to color it in one of the 4 colors. So it's a coloring assignment, shouldn't be too tough. It could be completed in Notability and uploaded that way. Or like I said, It could also be printed out and completed that way and then scanned back in. I hope you find this e-learning not too difficult. Have a great day. We'll see you later.